Alright, welcome back to our third part of the lecture today. We're going to talk now about how temperature changes with respect to height. Now, I wrote on here that we don't really tend to think about that very much in meteorology, but that's not exactly true. We don't talk about it in this context in the atmosphere. Actually, how temperature changes with respect to height is going to be very key to a concept called stability, but we're not going to be learning about stability until I think it's the 6th module in the course. Rather, in this context, we tend to worry more about a quantity called the environmental lapse rate, which is very related to the idea of temperature. But right now, talking about like, oh, where in the atmosphere is it 40 degrees Fahrenheit or 10 degrees below 0 Fahrenheit wouldn't be a useful thing. The same temperature appears lots of different places in the atmosphere. That wouldn't necessarily tell us anything interesting about how the atmosphere works. Rather, from our point of view, an important thing to know is about this quantity, the environmental lapse rate, or ELR. We're going to see this word lapse rate come up lots of times in this class. This first time that we see it is in the context of the environmental lapse rate. And if I wanted a dictionary definition of environmental lapse rate, I would say that it is the rate at which temperature changes with respect to height. Now, again, we're going to see lots of different lapse rates over the course of the semester here. What I mean is, like, if we measure the height here at this height, and then we measure the temperature at this height, and then we measure it at some second height, how much did the temperature change over that distance? Okay? It's something that we measure. We measure this with weather balloons and so on. We measure the temperature here, we go up to a new height, we measure the temperature here, there. From that we can figure out the rate at which the temperature is changing with respect to height. And this number is called the environmental lapse rate. It actually is a change in temperature over a change in height. You can measure this as a property of like layers of the atmosphere. We'd have then units of degrees Celsius per kilometer. Every kilometer, how many degrees Celsius did the temperature change? The weird thing about environmental lapse rate is that it is defined so that it is positive if the temperature is decreasing with respect to height. I didn't make the rules. I would have done it different. The environmental lapse rate is defined to be a positive number if the temperature is getting colder with respect to height. You'll kind of see why a little bit later. And it is defined to be negative if the temperature is getting warmer as you go up in the Earth's atmosphere. So what I want to do here is I want to show you a typical temperature profile in the Earth's atmosphere from the surface up to a height of about 140 kilometers. You have a figure very similar to this in your textbook, and you are responsible for understanding this temperature structure that we're going to be seeing here. Notice that there are layers of the atmosphere where the temperature is increasing with respect to height, and there are layers of the atmosphere where the temperature is decreasing with respect to height. This might be a good time to sort out this business of levels and layers. A layer of the atmosphere has thickness. There is a top to it and a bottom to it, and stuff happens between those two places. A level is just a height above the ground. Okay? So we're going to be dividing the atmosphere up into levels and layers based on the environmental lapse rate. Now the first layer I want to talk to you about, we actually briefly mentioned like in the ozone lecture, and that is the troposphere. The troposphere is the lowest layer of the atmosphere. It goes from the surface to about 10, 11, maybe 12 kilometers above the ground. And everything that happens in the atmosphere that you think of as weather, you know, snow and tornadoes and thunderstorms and whatever, all of that happens in the troposphere. In fact, that's the origin of the word troposphere. Tropo means turning or mixing. Yeah, you can think about words you might know that have the connection to this word tropo in your life. Throughout the depth of the troposphere, in general, temperatures are decreasing with respect to height, which means most of the time in the troposphere, the environmental lapse rate is going to be positive. Remember, we defined the environmental lapse rate to mean that the temperatures are decreasing with respect to height. So in the troposphere, the environmental lapse rate is positive. The troposphere is a layer. It has a bottom, namely the surface, and a top at about 10 or 11, 12 kilometers. And that top is a level of the atmosphere called the tropopause. The top of the troposphere is the tropopause. You'll see that that's a pattern. Now, the stratosphere is a layer of the atmosphere that sits on top of the troposphere. It spans from about 10 kilometers above the ground to about 50 kilometers above the ground. And in the troposphere, temperatures get higher with respect to height. The farther above the ground you get, the warmer it gets. That was really surprising in the history of meteorology. In meteorology, we started off by just understanding near the surface and doing simple experiments using towers and things like that, and maybe some simple balloons. And early meteorologists had never experienced a situation where temperature was increasing with respect to height. when they started discovering things like the stratosphere, they had to think of a word to describe that, and they came up with this term temperature inversion, or more commonly just inversions, to describe that. An inversion is a layer of the atmosphere where temperature is increasing with respect to height, and the stratosphere is an example of an inversion. Okay? When early in the history of observational meteorology they first discovered it, they were astonished by this. They didn't understand how this was possible. They thought temperature always decreased with respect to height. The stratosphere, as we discussed in the ozone lecture, is where the ozone layer is found, and it is very, very smooth. There's not a lot of weather in the stratosphere. In fact, this is why, in general, jumbo jetliners tend to try to fly in the lower stratosphere, because there's very little turbulence and very little storminess and so on for them to fly through. It tends to be a very smooth and efficient flight. The stratosphere is a layer. The bottom of the stratosphere is the tropopause. The top of the stratosphere is the stratopause. Notice the pattern again. The top of the troposphere is the tropopause. The top of the stratosphere is the stratopause. Mesosphere is the layer above that. It goes from the stratopause up to another layer a level called the mesopause. The mesosphere itself spans from about 50 kilometers to 90 kilometers. It is another place where temperature is decreasing with respect to height, so it is not an example of a temperature inversion. Here's the reality. Not a heck of a lot happens in the mesosphere. The mesosphere is not a particularly interesting part of the Earth's atmosphere. Some things about like where certain kinds of meteors burn up happen in the mesosphere, depending on their size and so on, but by and large the mesosphere is kind of an uninteresting place in the Earth's atmosphere. And finally there's the thermosphere. Sitting above the mesopause and extending up a few hundred kilometers up into the Earth's atmosphere is the thermosphere, starting at about 90 kilometers on up. It is once again a temperature inversion. Temperatures are increasing with respect to height in the thermosphere. So once again, the environmental lapse rate is negative. It is a temperature inversion. And temperatures get very, very high up in the thermosphere. The thermosphere extends to maybe 500 kilometers up, and those temperatures of those air molecules at those heights are a couple hundred degrees Fahrenheit. Wait a minute. We're like a couple hundred kilometers above the ground? Doesn't the space station orbit at like 300 kilometers above the ground? Yes. I thought the space station was in space. Yes. These are very thin layers of the Earth's atmosphere. There are very few molecules up here. Each individual molecule is very hot and carrying a lot of kinetic energy, but there's very few of them. I mean, in fact, if you walked out of the International Space Station, your body would be losing more heat by radiation than it is absorbing by all these air molecules out there. But in fairness, I mean, the International Space Station, the space shuttles, etc., they fly in a layer of the atmosphere. Okay? It's still much more dense. The atmosphere is still much more dense at the level of like the International Space Station than it is out in the interplanetary space. Okay? Oh. Alright, so you do need to know all about the different levels and layers of the Earth's atmosphere as stratified by the environmental lapse rate. Troposphere, tropopause, mesosphere, mesopause, stratosphere, stratopause, thermosphere. There is at a top to the thermosphere. Alright, there is one other way we can divide the Earth's atmosphere up into levels and layers, and that is based on chemical composition. I told you in the first lecture that there were these constant constituents of the Earth's atmosphere, like nitrogen and oxygen, that occur in the same ratios, nitrogen 78%, oxygen 21%, everywhere in the Earth's atmosphere, no matter where you went. A nice example of me telling you something and then you find out that that's not exactly the truth. That's true everywhere in a part of the atmosphere called the homosphere. The homosphere is the part of the atmosphere where the constant constituents are well mixed. And it extends from the surface of the Earth up to about 100 kilometers, which is pretty darn high. I mean, basically you're in space at 100 kilometers above the ground. The top of the homosphere is strangely named the turbopause, but that is the height when you transition from the homosphere into the heterosphere. From 100 kilometers, the turbopause, on up in the Earth's atmosphere, you're actually in a part of the atmosphere called the heterosphere. In the heterosphere, the constant constituents of the Earth's atmosphere, like nitrogen and oxygen and so on, are no longer well mixed. They tend to settle out. So you'll pass through a layer that is mostly nitrogen, and then you'll pass through a layer that's mostly oxygen and argon and so on as well. Again, keep in mind, we're not talking a whole lot of molecules here. This is going to be pretty thin. The pressure is basically going to be 0 millibars. but not quite 0 millibars, there still are some molecules up there at those very great heights above the Earth's atmosphere. So just to review, we saw how pressure changes with respect to height, how temperature and moisture and the environmental lapse rate change with respect to height, and also how the chemical composition of the Earth's atmosphere changed with respect to height. Let's ask 3 more quick questions here. Question 7 is actually very typical of a number of questions I know are in the test pool. Put these features of the atmosphere into order from lowest to highest. Tropopause, Mesosphere, Stratopause, Troposphere. These kind of sorting type questions are a great type of question to ask in an online test. Look through those 4 options and choose one of them, and then get a little feedback before you move on to question 8.